section 6.6. So let me finish off section 6.6 for you. Okay, 1 second. I had to move things around, so I sort of got tangled up. Okay, there. I'm untangled. Okay, so sorry about that. Let's start section 6.6. Not start. Let's finish section 6.6. Estimating the population mean and this is in the case when the population variance is unknown. Okay, so let's just recall that we have a t-distribution, and so if your variance is known, then we have a z random variable. The sampling distribution, maybe I should say that, the sampling distribution is normally distributed with mean and standard deviation given, whereas if the population variance is unknown, then the sampling distribution will be a t-distribution with degrees of freedom equaling n minus 1, where of course I would need to standardize the random variable to get that it's actually t. Okay, so we did an example and we finished it for, I'm sure we finished it. Yes, we finished it for looking at Kim and J. Okay, so let's start another example. So, example. Given that the sample mean is 16.8, the sample standard deviation is 4.1, and the sample size is 16, construct a 95% confidence interval for estimating the true population mean. Okay, so let me do that. So the confidence interval will have the form the best point estimate for the population mean, the sample mean, plus or minus an error. Since the population variance is unknown, then I'll have a t critical value times, well, the standard error. Well, the standard error, since I have a finite population, this will be sigma over the square root of n. Okay, so first off, I have to figure out what the critical value is. So I have that the degree of freedom n minus 1 is 16 minus 1, which is 15. Oh, darn. And so let me I have to go and look up a table. So let me go to EducaSoft. And let me look up my table. No, sorry. So let me look up a table here. Oh, good. Let me look up the T-table in Appendix 5. And so there'll be table number 4 in Appendix 5. So let me open that up. There it is. Okay. So if I look back, I had here degrees of freedom was 15, and I want a 95% confidence interval. So that means that 95% is going to be in the middle, which means that on each tail, I will have half of that. So 2.5%. Okay. So let me look this up in my table. And so I'll just look here in the second one. This third one, I guess, the third. And degree of freedom is 15. So let's go down to 15. There it is. And so it is 2.1314. Okay, so let's do that. And so my t-value, uh-oh, 1 second. Is everyone still able to see me? Everyone still able to see me and hear me? No. Okay, yeah, it blanked. So I had to move things around for a second. Okay. And now you should be able to see me. Okay, now it should be back. Can everyone see it now? Yes. Okay. So that was 2.1314, I believe. And so I have that the error is, well, t sigma over the square root of n is 2.1314. Yes, it will be at least as long as a regular session. And so will the one tomorrow. And so I don't know sigma, but I can approximate sigma by my sample standard deviation. So I had that sample standard deviation is 4.1 over the square root of 16. Okay, so let's multiply that out. So multiply by 4.1 by square root 16, you get 2.184685. Okay, And so my confidence interval, my 95% confidence interval for estimating the true population mean is just the sample mean, 16.8, plus or minus my error, 2.184685. And that is my answer. Okay, let me do it is 5 points. If you're asking about how much extra credit, how long is there? It is 5 points for every section that we cover, and so it could be a lot of points. So it's up to 5 points per section. So, if I cover 50 sections, that'll be a lot of points. I won't cover that many, of course, but however many sections I cover. Okay. And that depends on your, depends, of course, how good your lecture notes are for me. Okay, so let's do another example. The average and standard deviation of the weights of 100 accompanying bags of international travelers are 120 pounds and 25 pounds, respectively. Construct a 80% confidence interval for the average weight of accompanying bags on international flights. Okay, so let's do this. So in this case, n is 100. The mean, sample mean, is 120. The sample standard deviation is 25. And I want to construct an 80% confidence interval for estimating the true population mean. Okay, so I have here an 80% confidence interval. Since I do not know the population variance, this is going to be a t. The sampling distribution for all possible sample means will be a t distribution. This is 80% in here. Therefore, in each tail, it's 10%. Okay. My degrees of freedom are 24. Okay, so let's look this up in my table. And so 10%, and it is 24. And so 1.31, so 24. 1.3178. Sorry. Okay, so it is 1.3178. Okay, good. Okay, so the confidence interval. Wait, there are 100. The standard deviation was 25. I'm sorry. There were 100. So it was 99 was the, sorry about that. 99 was the degrees of freedom. So let's go down to 99, 10%. So 99 says 10%. We don't have 99. Okay, so it should be somewhere close to that, but we don't have 99. What we do have is, I have the z value. I can use the z value at least. Okay, so, oops. Okay, so for the z value, I had that the z value was 12, so 2816. 2816. So that would be the corresponding z value. Now I can use the normal approximation. To t to approximate what t is. And so I know that c equals z, 8 nu plus 3, 8 nu plus 1. And so I have 1.2816, 8 times 99 plus 3, 8 times 99 plus 1. Let me plug that into my calculator. And so 1.2816. So if I plug that into my calculator, I get 1.28483282. Okay, so now let's plug that into my formula. So I have that t is equal to the sine of z radical nu e to the c squared over nu minus 1. So this is equal to, it's going to be, I'm just going to take the positive one, so I'll make it positive. So the square root of 99 e to the 1.284832282 squared divided by 99 minus 1. Plug that into your calculator. Let's see what you get. So square root e to the over 99 minus 1. Okay. And so you get 1.2990206,979. Okay, good. And so my confidence interval has the form sample mean plus or minus my error. I know what the sample mean is. The error is going to be the t critical value times the standard deviation for the sampling distribution of all possible sample means, which is sigma over the square root of n. And so I get 1.290206979 times, well, we don't know the standard deviation, but we do know that the sample standard deviation was 25, and the sample size was 100. So let me multiply that, and so you get times 2.5. You get 3.225517448. Okay, so we get that the confidence interval the 80% confidence interval is just the sample mean, which was 120, plus or minus the error, which we calculated to be 3.225517448. And that is your 80% confidence interval. It's pretty small. Okay, good. So that really finishes off section, whatever it was, 6.6, I think. Yeah, 6.6. So let me start section 6.7. Okay. So already 5 points. Section 6.7, estimating the population proportion P, and this will be for large samples. Okay. So let's recall some things. That the expected value, the the mean for the sampling distribution of all possible sample portions is the population proportion. The variance, well, for the binomial case, So if I have that I have an infinite population, or we're doing a simple random sample with replacement. So the binomial case, we have that the variance of the sample mean, the variance for the sampling distribution of all possible sample proportions, that this is just equal to PQ over N. And if I have a finite so the hypergeometric case, if I have here a finite population and we're doing a simple random sample without replacement, then the variance for the sample proportion, the variance for the sampling distribution of all possible sample proportions is just PQ over N times this finite population correction term. Okay. The best point estimate for estimating the true population mean is just a true population proportion is just the sample proportion. If n is large, so if np is greater than 5 and nq is greater than 5, then, well, the binomial distribution can be approximated by a normal distribution. And the hypergeometric distribution can be approximated by a normal distribution. So for, and of course, these are both with continuity correction. Maybe I'll pull this over. So this is with continuity correction. Okay. And of course, if n is sufficiently large, in this case, we have that the confidence interval is just the best point estimate, the sample mean, plus or minus an error, where your error is, well, since I'm assuming that these conditions hold, then this will be approximated by z value. By z, I'll have a normal approximation, so the critical value will be a normal z value times the standard error given by one of the above formulas, depending on if it's a hypergeometric distribution or a binomial distribution. We also had the sample size. By the above formula, you can calculate the sample size. Well, for the binomial case, simple random sample, with replacement. We have that the sample size is z squared pq over e squared. Z squared pq over e squared. And for the hypergeometric case, so finite population and simple random sample without replacement, we have that the sample size is just equal to n z squared pq over e squared n minus 1 plus z squared pq. Okay. So let's do some examples. Let n equal 64. Let the sample proportion equal 0.3. I want to construct a 95% confidence interval for estimating the true population proportion. Okay, so let's do that. Okay, so first thing is, let's see if the normal approximation to the binomial distribution. Notice that this is a binomial distribution. This has a finite population because the population is not specified, and we're doing a simple random sample without replacement again because the sampling technique is not specified. And so let's first check if the normal approximation is applicable. Okay, so let's check this first. So let's look at n times p. Well, n is 64. I don't know p. Obviously, I don't know p. If I knew p, then I wouldn't be doing a confidence interval. But I can estimate p by the sample proportion. So the best point estimate for the population proportion is sample proportion. So I'll use that fact here. So 19.2, and that's certainly greater than or equal to 5. So that's okay. Next, n times q. Again, I don't know the population proportion of failures. I'll estimate it by the sample proportion of failures. So if there's a 30% chance of success, there's a 70% chance of failure. And so I get 44.8. And that again is greater than or equal to 5. So I can use the normal approximation. Therefore, my confidence interval will have the following form. So I couldn't even tell that this is the form until I did the showed that the approximation worked. Because actually this formula is wrong if this doesn't work. And well, let's E is equal to, well, again, since the normal approximation is applicable, then it's just going to be a Z. So as long as the conditions hold for a normal approximation, we'll always have the critical value will always be Z, because we're assuming that the normal approximation is applicable, times the standard error for the sampling distribution of all possible sample portions. And, well, that's going to have the form PQ over N. Again, because this is a finite population. Okay, so let's look up for 95%. Oh, well, we already know that. For a 95% confidence interval, the critical value is going to be 1.96. We could look that up here. There it is right there, 1.96. That is, oh, there it is. So that says there's 2.5% on each side, meaning the total on each combined of the two tails is 5%. Therefore, what's in the middle is 95%. And so that is the critical value for the normal approximation. I don't know P, but again, I'll estimate it. I'll estimate it to, where's the square root in this formula? Okay, I will estimate P to be 0.3 using the sample proportion, Q to be 0.7, again using the sample proportion, and N to be 64. And so if I plug that into my calculator, I get 0.112273,105. Okay, and so my confidence interval is 0.3, the best point estimate, plus or minus my error, 0.112273,105. And that is my confidence interval for estimating the true population proportion. So this is my 95% confidence interval for estimating P. Let me do another example. So let's say here n is much smaller. Say n is 12 or something. And I'll use the same one. So say, okay, so let's say that n here is 12, 3.6, so it won't work. And the sample proportion is 0.3. Construct a 95% confidence interval for estimating the true population proportion. Okay, so let's do this. First note, I can't use a normal approximation. So if I try what I did above, it's not going to work. Again, this is a binomial distribution. Because this is a finite population, because it's unspecified. And we're assuming, and again, since selection isn't specified, so it's a simple random sample without replacement. Okay, so let's look at n times p. Well, n is 12. Don't know p, but I can estimate the population proportion by the sample proportion. And so I get 3.6, and that is not bigger than 5. So that means we cannot use the normal approximation. So that means that this sort of simplifying technique is just not available in this case. So what we have to do is we've got to look in the table. So I'm going to have to look to see, and I'm going to, well, sort of draw it here. It's really going to look like a whole bunch of little things like this because there's 12 of them. 1, 2, 3, 4. So they're going to be like 12 of these here. 13. 0, 1, 2, 3. That doesn't really look like it's in the middle. 4, 5, 6, 7, 8, 9, 10, 11. I should have picked something smaller. 12. Okay, so if I look here in table, go back more, in the binomial table, table 2A, there it is. And let's look for, I said, what's it, 12? I should have picked a smaller number so it wouldn't be so big to look at. 12. Oh, no, there's 12. That's not too bad. Okay, so what I have to do here is I'm going to have to, so I notice that this is 95%. So that means that each tail will be 2.5%. Each of my two tails. So what I have to do is I'm going to have to add up each of these till I get to 2.5%. Ooh, well, that's less than 2.5%. But if I add these two together, that's more than 2.5%. And so that's 0.14. And that's in the, that's outside of my confidence interval. That's my tail. But if I go any further, it'll be too big. Let's look on the other side. Notice confidence intervals are always symmetric about each side, but the actual interval may not be symmetric. In this case, it won't be because, well, n is too small. So it's not a symmetric distribution. So let's do another 2.5% on the other side. Well, and I did pick 0.3, right? Yes, it is 0.3. Okay, so whole bunch of zeros here. That's 1. Add that to give you 9. Too big for that. That'll give you more than 2.5%. So 8 and 9. So 8, 8, 1, and then 3 zeros. So if you add up these areas here, you get less than 2.5%. Okay. But if you add up another one at 7, it would be too big. Okay, so, and let me just check. Yeah. So that means that my confidence interval are these numbers. So this is my 95% confidence interval, will be all of these numbers. And so my confidence interval are the numbers, well, let's do it with the inequalities, between 0 and 8. So I don't want to do it for the binomial random variable. I want to do it for the sampling. So let's divide each of these numbers here by 12. If you do that, 12 because n is 12. If we do that, then we see that we get a sampling distribution. A sampling, so 8 will give you, 8 will give you, okay, so that will give you 0 less than, so my confidence interval less than 2/3. So this is my 95% confidence interval for estimating the true population proportion. So notice that if we do not assume if we cannot use the normal approximation, then what you'd have to do is actually go out and do it for the actual distribution. So this technique was just a technique that we used because n was sufficiently large. Okay, so if n is sufficiently large, we can use some sort of technique to approximate it. Otherwise, we really can't. Actually, I did this without continuity correction. I should have done a little bit of continuity. I should have done some continuity correction here. But the problem is that for confidence intervals, it's kind of hard to do continuity correction because there's errors on both sides. Okay, let's do another example. Any questions about what I just did? No. Okay. Nope. Okay, good. Let's do another example. N is 300. X is 70. I want to construct a 95% confidence interval for estimating the true population proportion. Okay, good. So let's do this. So n is 300, x is 70. Let's see if the normal approximation is applicable. So let's check. And so NP, N is 300. I don't have P, but I do have some sample data. So I can calculate the sample proportion from that, which is just X over N. And well, that's greater than 5. Let's calculate NQ. Again, I have N, but I don't have Q. I can use the sample proportion of successes. If I have 70 successes, I have 230 failures out of the 300. And so this is also greater than or equal to 5. So that's good. The normal approximation is applicable. And so my confidence interval will have the form P plus or minus an error. Okay. And so this is 95%. Therefore, on each side, it's going to be 2.5%. And well, we already looked, and I think I can just, hopefully I looked up above. So for 95% confidence interval, we already did that, and the z value was 1.96. Oh, where did I get that? Sure. If I have 70 successes, then out of 300, then 230 of them must have been failures. So I just use the fact that I had 70 successes. Okay? That's the number of failures. Okay. So negative 1.96. Okay. Let me try to invoke continuity correction for you. Okay. Okay, so x was 70. Oh, but you won't know which side it is. Sorry, because you won't know. So this and that end. Okay, here, wait 1 second. Okay, so for this end, you would subtract a half. For this end, you would add a half. To the successes. Yeah. They feed off of each other. Okay, so let's just not invoke continuity correction. Sorry about that. So let's do this without. So we should be doing continuity correction. Unfortunately, the continuity corrections are going to start to cancel each other out, and they'll be very complicated. Okay, so I have that the error is equal to, well, since the normal approximation is applicable, z times the standard error for the sampling distribution of sample proportions, which will just have the form PQ over N. Okay, so my error is equal to Z 1.96 times the square root of P. Again, I don't have P, but I do have a sample proportion. 70 over 300 are successes. Again, I don't have Q, but I do have the sample proportion of failures. If 70 are successes, 230 out of the 300 are failures, and n is 300. So you plug that into your calculator, and you get 0.47861591. So I get that my confidence interval is equal to, again, I should say that my sample proportion is x over n, which is 70 over 300, which is 0.23, a whole bunch of threes. Therefore, my confidence interval is the best point estimate for my population proportion, the sample proportion, 0.2 with a whole bunch of threes, plus or minus my error, which is 0.047861591. And that is my 95% confidence interval for estimating the true population proportion. Okay. Let me do, I see I did another one. Yeah, let's do that. Example. Let n equal 25. The sample proportion, 0.3. I guess, don't know why I'm always doing 0.3. 0.3. I want to construct a 90% confidence interval for estimating the true population proportion, P. So let's do this. So let's check if the normal approximation is applicable. So let's do n times p. So n is 25. Again, I don't know what p is, but I can estimate p. I can say, well, it's approximately equal to the sample portion. So 7.5. That's greater than or equal to 5. Let's look at n times q. Again, I don't know what q is, but I can estimate it by the sample proportion of successes. So if there's 30% chance of success, there's a 70% chance of failure. And so I get 17.5. Not too bad, not too good. And so this is also greater than or equal to 5. And so this says that, well, good enough. My confidence interval is just a sample portion plus or minus my error. And so, that's point. My error is going to look like z times the standard error. And so z pq over n. Okay, so we're doing a 90% confidence interval. We've actually done this before, I'm pretty sure. And so that's 5% on each side. Let me just check. Above. See if I have 90% anywhere. If not, I'll look in the table. I did 95%, 95%. No. Okay, so let's look in the table for 90%. Okay. And so that'll be the second. So 5% on each side gives you a 90% in the middle. So if I look here at the very bottom of my table, 1.6449. And that is your Z value, your critical value. And so your error is equal to 1.6449 times the square root of, again, I don't know what P is, but I'll estimate it by the sample proportion. I don't know what Q is, but I'll estimate it by the sample proportion of failures. And N here is what, 25. So let me do that on my calculator. Point 150757. Okay, and so my confidence interval will be 0.3 plus or minus 0.1507575 and that is my 90% confidence interval. Okay. Actually, this is small enough. Let's do this without doing. So let's see my confidence interval. Let's write it where I add and subtract. And so this is equal to 0.1492424 and 0.450757572. So if I write it in this fashion, it'll be easier for me to check. Okay, so let's do this without the normal approximation. So we can sort of check. So let's do this example. N is 25. The sample portion is 0.3. And I want to construct a 90% confidence interval for estimating the true population portion. And let's do this without using the normal approximation. So this will just be doing it the way you're supposed to do it, without actually using an approximation. So let's do this. Okay, so I can look. So this goes from, 25. That's a lot of numbers. Can't even fit them all. Okay, so I have a whole bunch of these probabilities. And I want that if you add each of these tails up, it's 90%, so these got to be less than 5% when I add them up. Okay, oops. Look in table 2A. So 25. Okay, so 25, good. And we're doing 0.03, so I can add these up. Probably 57, that's too big. I can add these up. Obviously zeros. I can add up these. 27 will make it. 54 is too big. Okay, so I can add up all these. So I have here, this is going to be a 0. That'll be a 1, 7, and then I think it was 24, right? And then there were a whole bunch of zeros till you got to 15. So there are a whole bunch of zeros there. And then 1, 4, 1, 4, 11, 27, 7. Okay, good. Eh, 15 was 1. I think I messed up. Eleven's 27. No, 11's 54. There is no 7. Okay, 24, 11. Okay, uh, so if you add up all those, so that's going to be 35, 39, 40.4. So that's good. So adding up all these areas, you get 0.4. Adding up all these areas, you get 0.032. But if you go any further, you'll actually get something bigger than 0.05 on each side. Each of these had like 0.054 or something, something quite huge. Okay, so my confidence interval therefore looks like numbers between 4 and 11. Let's do inequalities. Okay. So if you divide everything by 25, 0.48, and so you get somewhere between 12 and 48, which isn't bad actually. Okay, so we said it was between 12 and 48. Here it says it's between like 14 and 45. So it's not too horribly bad. Obviously, it's off by a little bit, but and so doing it by hand, well, obviously, doing it from the actual table without approximations will give you the actual answer, and the approximate answer, n is pretty small, will give you something close, but obviously not exact. Let me do another example. I want to determine the probability that my sample proportion is between 0.24 and 0.332, given that I'm doing a binomial random variable with 500 trials and probability of success of 0.28. Okay, so let's do this. So first let's check if the normal approximation is applicable. So the normal approximation to the binomial distribution. So n times p. N is 500. P is 0.28. And so 140. That's certainly greater than 5. If I have a 28% chance of success, I have a 72% chance of failure. And so 360. Again, that's bigger than 5. So let's invoke continuity correction. So let's do that. So I have here, I'm at 0.24 and 0.32. And so, and there's other stuff besides that. So I'm going to have to add but it's less than, but it's here at 0.24, and it's here, I'm sorry, because oh no, that's right. because it's equal. Okay, so it's here at 0.24 and here at 0.32. Okay. Okay, so I'm going to have to add 0.5 over n, which is 500. Okay, and so if I do that, I get 0.241. Here I'm going to have to subtract 0.5, and so 0.319. And so I get that I want to calculate the following. Probability x is between 0.241, the sample proportion, and 0.319. So let's determine my parameters for the normal approximation. And so the mean for the sampling distribution of all sample proportions is the population proportion, and the population proportion was assumed to be 0.28 from the above assumption. The standard deviation for the sampling distribution of all possible sample proportions is just equal to radical PQ over N. Again, P is 0.28, Q is 0.72, and is equal to 500. Plugging that into your calculator, you get 0.020079,841. And so let's determine that's standardized. My normal random variables. And so z equals x minus mu over sigma. And so z is equal to 0.241 minus 0.28 over 0.020079,841. And so you get negative 1.942246455, and you get z equals 0.321. No, 0.319 minus 0.28, 0.020079 841. Again, plug that into your calculator. $1.942246.455. Okay, good. And so I want to figure out the following. Probability that z is between 1.942246.455 and positive 0.942246.455. Yes. Tad bit. Yes, yes, you may. Good, and just tell me when. Okay. Now I'm caught up. Okay, there it is. Good. Okay. Okay, so let's look these up in my table. Okay, so in table 3, I'm going to use linear interpolation now to determine this area. So I have here 1.9 4 5. Okay, so 1.9 4 and 5. That's that one. So 4738. And 44. Okay, so let's do that. No, I guess let's use this. So P equals P1 plus P2 minus P1, Z2 minus Z1, Z minus Z1. Okay. And so 0.4738, 4744. Ooh, there's no way I can fit all this. Four, 4744, 4738, 1.95, 1.94, 1.942246.455 minus 1.94. Okay, so plug that into your calculator. Let's see what we get. 0.4739347873. And so, and let's call this A. The area I'm trying to compute. Oops. This area. (1.942246455) negative 1.942246455. I just add up both of these areas. So the probability that your sample portion is between 0.24 and 0.32 will just equal, well, each of these areas added up. So you get 0.94786954746. Let's do another example. It is believed that 55% of patients coming to suburban HMOs are females. If a random sample of 300 patients at the clinic are selected, find the probability that less than half will be female. Okay, so let's do that. So n in this case is 300. Success in this case is that the patient coming to the HMO is a female. The probability of success, well, we're assuming that it's 55%. Okay. And I want to figure out the probability that less than half are female. And so 0.5, that the sample proportion is less than 0.5. Okay, so let's first see if the normal approximation is applicable. So let's check. Okay, so n times p, 300 times 0.55, 165, is greater than or equal to 5. And so that's true. N times Q, if 55% are successes, then 45% are failures. And so 135. So again, the normal approximation is applicable. Let's invoke continuity correction. And so we have less than 0.5. So here's 0.5, and it's got to be less than it. Okay, so I'm going to have to subtract. So 0.5 minus 1/2 over n. So that's going to be 0.498. It's a whole bunch of 3's. Okay. So I want to find the probability that some portion is less than 0.5. So after invoking continuity correction, I want to find the probability that this normal random variable is less than 0.498, which is a whole bunch of 3's. And so let's determine my parameters for the normal approximation. So I have here that the mean for the sampling distribution of all sample proportions is the population proportion, which was assumed to equal 0.55. The standard deviation for the sampling distribution of all sample proportions is just radical PQ over N. So if I have 55% chance of success, I have a 45% chance of failure, and I had N was 300. Plug that into your calculator. So you get 0.028722813. Okay. So let's standardize. And so Z equals X minus mu over sigma. And so I have 0.49833 minus 0.55 over 0.028722813. Plug that into your calculator. So you're going to get negative 1.79880245. And so I want to find the probability that the sample portion is less than 0.5. And so that's the same as finding the probability using the normal approximation that z is less than negative 1.798802.445. So I'm going to use linear interpolation. Okay, so let's do that. So I want to find the area of this tail. And so let's call this A. So let's look at 1.79 and 1.78. I don't know how to note. So the other one's 1.8. So this will be 1.79 and this will be 1.8. It goes across the ends of it. So if you look, .79, there it is. So here's 1.79, 4633, and 1.8, 4641. Oh, okay. So 4641, and the other was 4633. Okay, so I have that P equals P1 plus P2 minus P1, Z2 minus Z1, Z minus Z1. I guess I'll call this A, is 0.4633, 4641, 4633 over 1.80 minus 1.79 times 1.798802.445 minus 0.79. Plug that into your calculator. 0.4640041956. So the probability that the sample proportion is less than 0.5, that less than 50% are females. 0.5 minus A, 0.0359958.044. So there's around a 3.5% chance that less than half are females. Okay. So let me do the following example. Okay. Many companies are interested in knowing the percentage of adults who buy clothing online. How many adults? must be surveyed. In order to be 95% confident that the sample percentage is an error by no more than 3 percentage points. A. Use the result from the Census Bureau that 66% of adults buy clothing online. B. Assume that we have no prior information suggesting a possible value of the proportion. Okay, so let's go and use these formulas we had for estimating the sample size. So I had some, way up at the top, I had some formulas for the sample size. Here it is. Now, if you don't know P or Q, you use, so if P is unknown, use the sample portion. If the sample portion is unknown, use 1/2. So use a half, 0.5. That will give you the maximum error. So just use 0.5. So here it is. So let's do this. Okay, so in this first case, I have n is equal to z squared pq over e squared. Well, we're doing a 95% confidence interval, and as we've seen above, the z value for 95% was 1.96. Square that. I don't know what P is, but I do know a sample proportion. So I'll use the sample proportion 0.66. If 66% are successes, 34% are failures, and my error is 3%. So plug that into your calculator, and you get 957.8389 and a whole bunch of threes. And so my sample size is 958. Well, suppose that I don't have an estimate at all for my population proportion, in which case I'm just going to estimate P by 0.5. Of course, I have 50% chance of success. I have 50% chance of failure. And then plug that into my calculator. So if I do that, I get 1067.1. And so n is equal to 1068. So you notice that even if I don't have an estimate, I can still estimate it by just plugging it in half. They'll give me the largest number of possible people I should survey, which actually isn't that much more. So you would ask around 1,000 people. Okay, let's do one more. Suppose you wish to conduct a sample so that you are 90% confident that you have an error of less than 2% for estimating the population proportion given that in a previous survey it was found that the sample proportion was 0.42. Okay, so let's do this. So n is equal to z squared pq over e squared. So this is a 90% confidence interval, which we found for 90%, 1.645. Oh, this is 1.6, well, 1.6449. Okay, 1.6449. So let's do that. So 1.6449. P is 0.42. Q is 0.4858. And E is 0.02. Plug that into your calculator. And so you get 1,647.76887. And so I have that N is equal to 1,648. So as you notice, our sample sizes keep being, well, just about the size of samples that we found when we looked at, what newspapers and other people survey. They're around somewhere between 1,000 and 2,000 people. So, okay, so that finishes off section 6.7. Let me look at section 6.8. Yeah, I know, that's right. Section 6.8. Oops, wrong thing. Um, we actually can't have break time, just because break time doesn't really do well on an online session. Um, okay. Section 6.8. Estimation. Okay. Sure. Okay. Estimate. Uh, estimate. So it's estimation of the sample variance and sample proportion. Of the population variance and population proportion. So the population proportion and the population variance and the population standard deviation. So estimation of population variance and population standard deviation. Okay, so it turns out that, so let's look at the sampling distribution. Well, of sample variances. So the sampling distribution of sample variances is the probability distribution of all possible, all variances, all sample variances from all possible samples of size n, of sample size n. So you take all samples of sample size n, compute all the sample variances. That probability distribution is called the sampling distribution of sample variances. Okay, so we're going to introduce yet another distribution, the chi-square distribution. It turns out if you look at the sampling distribution, the sample variances, it will follow what's called a chi-square distribution. The chi-square distribution is not going to be symmetric. It's going to be positively skewed. Oh, and that's the symbol. It's the chi, that Greek letter chi, and with a exponent of 2, so it's a chi-square distribution. The distribution will depend on the degrees of freedom. And so this distribution here depends on the degrees of freedom. Well, let's recall again the gamma function. And so the gamma function, as always, is just the area under the curve for positive values of x to the t minus 1 e to the minus x. It is just an extension of the idea of factorial. And so for any integer, for any natural number value n, gamma of n is just equal to n minus 1 factorial. And so the chi-square distribution has the following probability density function. So it's just equal to some constant, so that this will always come out to have an area of 1. So 2 to the nu divided by 2, sigma to the nu, times gamma of nu divided by 2, times, well, the variable chi-squared to the power nu over 2 minus 1, times, well, e to the, now it looks like the normal distribution, e to the negative chi-squared over 2 sigma squared. So it turns out that if you look at the sum of the squares of normal random variables, the sum of squares of normal random variables will follow a chi-square distribution. The expected value, so note, the expected value of chi-squared is just nu. The variance for chi-squared random variable is just 2 nu. The mode is nu minus 2 for obviously degrees of freedom greater than 2, and the skewness is radical 2 over nu. The test statistic is just chi-squared is equal to the ratio of variances. It's just the degrees of freedom times the sample variance over the population variance. Okay, so we have some approximations for the for chi-squared. So the normal approximation to the chi-squared. So first, the Wilson-Hefferty approximation, and this is an excellent approximation. Much better approximation than you've seen for any other situation. So the Wilson-Hefferty approximation. So it's an amazingly good approximation. Chi-squared is equal to nu 1 minus 2 over 9 nu plus z radical 2 over 9 nu cubed. And, well, I say it's true for degrees of freedom greater than or equal to 5. But again, it's really true for degrees of freedom greater than or equal to 2. Okay. That far correct. Okay. Okay. I can scroll back down, that means. Okay, so that's a Wilson-Hefferty approximation. I also have the Fisher approximation. Again, these are named after people. So the Fisher approximation says that chi-squared is equal to 1/2 z plus radical 2 nu minus 1 cubed, no squared. And this is true for degrees of freedom, let's say, bigger than 200. Okay. We also have the chi-squared approximations to z. So we have the Wilson-Hefferty approximation. Hefferty approximation. So we have z is equal to the cube root of chi squared over nu minus 1 minus 2 over 9 nu over the square root of 2 over 9 nu. Again, this is true for degrees of freedom greater than 5. It's a very conservative estimate. So what this says is that if I look at the cube root of chi squared over nu, that's approximately normally distributed with mean of 1 minus 2 over 9 nu and standard deviation of radical 2 over 9 nu. Okay. Approximately. For, obviously, well, for nu large. And in this case, large means like bigger than 5. We also have the Fisher approximation. Which says that z is equal to radical 2 chi squared minus radical 2 nu minus 1, and this is true for degrees of freedom greater than or equal to 200. So this says that radical 2 chi squared is approximately normally distributed with mean of radical 2 nu minus 1 and standard deviation of 1. And this is true for large degrees of freedom, in which case pretty large, at least 200, if not much more, in order for this approximation to be anywhere in the realm of reality. Okay, so let's do some examples. So we're going to have to look things up in differing tables now. So first, suppose I have degree of freedom of 11. So given the degree of freedom of 11 and the area of the right tail, maybe I'll just sort of draw it. So let's find this. I have chi squared. Degree of freedom is 11. And the area of the right tail is 0.05. Whatever. Okay. Stop erasing. Okay. Okay, there. And so I want to find the value of chi squared. So let's look. Here it is. No, it's not. 2 more down. Yeah, there it's chi squared. Okay. So notice that this is the area of the right tail, and I wanted the area of the right tail to be 0.05, so there it is. And I look for my degrees of freedom, which is 11. And so if I do that, I get 19.675. And so 19.675. And that is your answer. Let me do another one. Given degree of freedom is 8, and the area of the right tail is 0.025, determine the value of chi-squared. So let's determine the value of chi-squared. So degree of freedom is 8, and the area of the right tail is 0.025. So area of the tail, right tail is 0.025, degree of freedom is 8, and so 17.535. And that is your answer. Let me do another example. Degree of freedom. Uh-oh. No, I didn't multiply anything. Nope, nope, nope. All I did here is I looked at, so the degree of freedom here was 8. Alpha was 0.025. So alpha here is 0.025. Degree of freedom is 8. And so I just read off this value, 17.535. So I'm just reading off values on the table. Okay. Okay, so let's see. Given that the degree of freedom is 15 and the area of the left tail is 0.95, so the area of this is 0.95, then that means the area of this is 0.05. Oops, hit the wrong one. Okay. um, Drink something. And so, uh, oops, error. Uh-oh, error. 1 second. I have to come back to you guys. I'll be back to you in 1 second. Now you should be able to see me again. I was out for 1 second, I think. Okay, so now, if the area to the left is 0.95, then the area to the right is 0.05. And so let's look at this. Degree of freedom is 15. And the area to the left is 0.95, therefore the area to the right is 0.05. And so my answer is 24.996. And that is your answer. Lastly, let's do this example. And so I want to determine the probability that chi-squared is between 0 and 7.769, given that my degrees of freedom is 5. Okay, so I look here, and I have that my degrees of freedom is 5. And I want to look for 7.769. And well, it's nowhere to be found. It's somewhere in between these two values, but certainly all these values are much too far from each other. So there's no way to use like linear approximation for this table. So for this particular table, linear approximation is not applicable, but I did give you some approximations that are applicable. So the reason that I gave you those approximations is because you really can't use linear interpolation. Okay, so let's do this. So let's use the Wilson-Hefferty approximation. So Z equals, so I guess I'll use the Wilson Hefferty approximation. And so Z is equal to the cube root of chi squared over nu minus 1 minus 2 over 9 nu over the square root 2 over 9 nu. Okay, so let's plug in. So cube root of chi squared is what, 7.769 from here. Degrees of freedom was 5. 1 minus 2 over 9 times 5 over the square root of 7.769. Oops. You don't put the chi-squared there. You put the 2 over 2 times 9 times 5. Okay, plug that into your calculator. And you get 0.9614143716. Okay, so I guess I'll use linear interpolation. And so this should be between 0.96 and 7. So let's look in our table. So between 9.6 and 9.7. So 33.15, 33.40. So 33.15, 33.40. Okay. And so let's use our linear interpolation formula. P is equal to P1 plus P2 minus P1, Z2 minus Z1, Z minus Z1. And so I have here 0.3315, 0.3340. There's no way I can do this. I'll probably call this A. So 0.3315 plus 0.3340, 3315, 0.9796, 0.9614, 143716, 0.96. Plug that into your calculator. and you get 0.3318535.929. Okay. Okay. So we want this to be greater than. So I have that the probability chi-squared is greater than 7.769 is approximated probability z is greater than 0.9614143716. And so I take this area here, A, between 0 and the 0.9614143716. And so I get the probability that chi-squared is greater than 7.769 is just zero point 0.5 minus A. Plug that into your calculator. You get 0.1618146471. Now, you could also do this on your TI-83. So it's just going to be the area less than this. So it's going to be, I don't think I drew it. So it's just going to be 1 minus this. Oops, I might be scrolling up too fast for everyone. No, because if you look here, it's positive, right? And so, you're saying if it's less than. Yes, I'm sorry. If you said less than, yes, you're correct. Okay, yeah. If it's less than, you would add 0.5. Okay. Um, and so let's just look here. Notice that this is the area less than this. So if I want to find the area greater than it, I have to subtract 1 from this. So it's 1 minus chi-squared CDF. And we start at 0. And we go to the 7.769. And my degrees of freedom are 5. So let's do that on my calculator. There it is. So I should do 1 minus, there it finally, get the distributions, go to chi-squared, which is this, actually it's the 8th one down. So the chi-squared here, chi-squared CDF. And you'll start at 0, and you'll keep going till you hit, so you go from 0, comma, 7.769. And then my degrees of freedom are 5. And you plug it in. And you get 16,943. Where is it? There it is. 16,943 44,118. Okay. So we did actually several approximations. So notice we did the Wilson-Hefferty approximation, which is a very good approximation. But then upon that, we also did linear interpolation, which made it a little further off. So we're still accurate to like 3 decimal places. So that's not, you know, or at least 2 decimal places. So we're not too bad. But doing 2 approximations in one calculation will make some difference, and obviously it did make a little bit of difference here. Okay, any questions about this? Okay, so let me give you some properties. For the sampling distribution for sample variances. So first is that the sample variances target the population variance. So the expected value of the sample variances, the mean for the sampling distribution of all possible sample variances, will be the population variance. Next, the variance for the sampling for the sample variance, the variance for the sampling distribution of all possible sample variances will be 2 times the square of the variance over n minus 1. Okay. So that says that the standard error, that the standard deviation of the sample variance, the standard error of the sample variances, the standard deviation of the sampling distribution of all possible standard sample variances is just going to be the population variance over radical 2 over the degrees of freedom. Okay. So, note the following. Even though, so from now on, we'll mostly be talking about variances. And the reason for that is that even though the expected value of the sample variances is a population variance, the expected value of the sample standard deviation is not the population standard deviation. So the sample standard deviations do not target the population standard deviation. Even though sometimes we'll just sort of punt and say, well, it's close enough, that's we'll just sort of use the sample standard deviation to approximate the population standard deviation. Okay, next, if the population is infinite and the n here is very large, then we have that the variance for the sample variances will be approximately 2 times the population variance over the sample size. And we have that if in addition the population variance is unknown, that the standard error is approximately the standard deviation times radical 2 over n. So that says that the confidence interval, again, this is for n very large, for the population being infinite and the sample sizes being very large. My confidence interval for estimating the population variance is really nice and symmetric. And it has this form. Okay. Now, the best point estimate for the population variance is the sample variance. A confidence interval for estimating the population variance. If you are sampling from a normal population. Well, it'll have the following form. Just be the test statistic. Nu times the degrees of freedom times the sample variance over the chi-squared value, and it'll be the right chi-square value, and degrees of freedom sample variance over the left chi-squared value. Okay. Please note that you must assume that we have a simple random sample, and the population must be normally distributed. And this is true even for large sample sizes. And so you can't be very far from normality in order to use a lot of these things that we're doing in this section. Okay. So let's do the following example. A simple random sample of 22 IQ scores is obtained. Construct a confidence interval for the, I guess I'll have to write it all out. A simple random sample of 22 IQ scores is obtained. Construct the confidence interval. For the population variance. Oh, no, it says construction of. So construction of a confidence interval for the population variance requires left and right critical values. of chi-squared. In this case, and we're going to do it for a 95% confidence interval. Corresponding to the confidence interval confidence level of 95% in a sample size of 12. Not of 12, 22. Find the critical chi-squared values. Corresponding to the 95% confidence level of confidence. Okay, so let's do that. So we have here a chi-squared distribution. And we have in the middle is 95%. And so on this end, I have total is 5% on the outside. So for each tail is 0.025. And actually for this guy on the other side, this whole thing going from 0 to this value will be the remaining 9.75. My degrees of freedom was 21, since I had 22. And so let's look this up. So I have 21, look in the wrong table. So I look at 0.025. Okay. And I look for 21. It's this one, 21. And so I get 35.479. Now, I could look over here at 0.975, but notice this is the first, second, third column. To find the corresponding one, you always go to the whatever. If this is the third column, you go to the third column on the other side. If this was the second column on the left, go to second column on right. And so I was at the third column, and I want to do 21, 10.283. So the right, let's do the left first. The left chi-squared value is 10.283. So that's what that L means, is that it's the one on the left. So this is the left one, and this other one will be the right one. So this is to the left of this value. The right one which is to the right of this, will be 35.479. And so those are your right and left. Okay. Okay, so next example is just construct the confidence interval for this guy. So example, construct the 95% confidence interval for estimating the true population variance for the above example. Okay. So I have that my formula is degrees of freedom sample variance over let's see, this is the smaller one. So we've got to have the bigger one. So it's the guy on the right. And degrees of freedom sample variance over the one that's smaller will give you a bigger number. And so that's the one on the left. Okay, so let's do this. My degrees of freedom, if you remember correctly, was 21. My sample given that with the sample variance, I forgot that, with the sample variance, a sample standard deviation of 14 with sample standard deviation of 14.3. Okay, so I have the sample standard deviation is 4.3, so I'm going to have to actually square that. Now, the chi-squared for the right was 35.479. Everything remains the same, except for the left chi-squared is 10.283. Okay, so plug that into your calculator. So if you do that, you get 121.0375 15498, and you get it 417.6106 19469, and that is your 95% confidence interval. Okay. Let me do another example. In a random sample of size 50. Yeah, I know. So we'll probably go for about another 5 minutes or 10 minutes. You want the extra points, so so I will do it. We'll finish off in about 10 minutes or so. I just have one last example, and then I'll finish off this section. So a random sample of size 50 from a normal population. The sample variance is 2.124. Determine the following. So point estimate. For the population variance. Next, 99% critical values for chi-squared. And last, a 99% confidence interval for estimating the true population variance. Okay, so, well, the best point estimate for the population variance is the sample variance. And the sample variance is 2.124. So you're done. Next, let's find the critical values for chi-squared. This is a 99% confidence interval. So that means that 1% total is on the outside. And so this is going to be half of 1%, 0.005. My degrees of freedom are 50 minus 1 is 49. So let's look in my table, 49.005. So 0.005 is the very last column. So 49, chi-squared. So 49 is not quite on the table. Okay, but that's fine. Okay, so you should use an approximation. And so let's use the Wilson-Hefferty approximation. Okay, and so I have that chi-squared is equal to nu 1 minus 2 over 9nu plus z rad 2 over 9nu cubed. Okay, well, let's do the positive one, which is to the right. So my degrees of freedom are 49. Defined, so this is 5% on the tail, 0.005. So 5.005, the second column, 49. And so I get 2.5758. 2.5758. 5758. Let's plug this into our calculator. 2 over 9 times 49. And so whoop, 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 whoop. You get 78.26356757. Now let's do it for the left. Well, notice for the left, by symmetry, the z-values can be a negative 2.5758. So that's the only difference in the calculation. And so chi-squared for the left is equal to 27.21534493. Okay. And so I have that my confidence interval, so that's the right and left ones. So for my confidence interval, I have nu s squared over chi-squared nu s squared over chi-squared. And so my degrees of freedom was 49. My sample variance was 2.124. Notice you don't square it. And my right was 78.26356757. My degrees of freedom is the same, 49. My variance was the same, 2.124, and the left was 27.21534493. And so if you plug that into your calculator, you get 1.329814.155. 3.824166,118. Okay, and really that finishes off. Determine sample size. There usually are tables you can look at, but I guess I'll leave it at that. So that really finishes off section 6.8. So tomorrow, I guess we'll go over, we'll finish off the rest of chapter 6, and then we'll get through chapter 7, because chapter 7 is actually pretty fast. Okay, then, I guess that's it for today, and we'll do it tomorrow. Okay, then. Bye bye now.